7:30 either. I'm Alan Treeman. I'm one of the staff scientists here at the Institute, and I'm going to introduce Walter, who is too modest to introduce himself and say how wonderful he is. So that's my job. Walter and I have been here for more than 30 years. We joined the Institute at about the same time back in the 90s. And in the meantime, he has worked himself up to the point of being director of the Institute now. Congratulations. Yay. Walter is primarily a scientist, a geophysicist, which means that he worries about physical processes inside the planets, primarily looking at gravity, which I'm sure he'll talk about here, that variations in the strength of gravity on a planet's surface can tell you a lot about the interior of the planet. And that's what Walter has done for most of his career, that and really intense computer modeling to try to understand what the signature you see at the surface means about what's way deep underneath. So he's applied this idea, this modeling of gravity all across the solar system. He's done it for Venus, for the moon, I think for the Earth, I'm not positive, but certainly also for Mars, and has had really quite an excellent career doing this, and has now moved into management, which he will eventually, I think, get back to doing science with the spacecraft missions. And he's been involved in a great many spacecraft missions. Those are sort of the holy grail in planetary science. You get to work with data coming straight from a planet, get to help operate a robot working on another planet or around another planet. It's just the absolute coolest thing you can imagine. I'm sure Walter would agree with that. So he's been worked with the Dawn mission that went to the asteroids Vesta and Ceres. I'm spacing out. He's with the Da Vinci mission, which is going to land on Venus. He's with the European Envision mission, which is going to orbit Venus. And now he's going to talk about his upcoming mission, which is to Europa. And so he's going to be telling you about wherever the title is gone, Europa Clipper, exploring the interior of Europa. So I give you Dr. Walter Kiefer.
Now let's see if I can get the slides up. Thank you, Alan, very much for that introduction. There we go. Okay. Can everybody hear me okay? Excellent. Okay. So I have two jobs tonight. As Alan said, I am part of the science team for Europa Clipper, which is, that makes me one of about 150 people altogether. It's a really big mission. But I want to do two things. I want to talk to you about why Europa, which is a moon of Jupiter, is an exciting place to go and why NASA is sending a spacecraft there. And then I want to tell you what the spacecraft is going to do. Okay. So let's start with why Europa. Jupiter has 4 large moons. It actually has something like, I've lost track, 80 or 90 small moons, but it has 4 moons that are about the size of Earth's moon or bigger. Europa is actually the smallest of those 4. They're called the Galilean satellites because Galileo saw them with the very first telescope, which was less good than but pair of binoculars you can buy at pretty much any sporting goods store or something. So these are big in comparison to the many little things that are out in the outer solar system. We've known for 45 or more years that Europa was a surprising and interesting place. Actually, probably going back to the mid-70s with Pioneer missions. Am I doing something wrong? Can't see my slides where. Oh, that's interesting. Okay, we'll try it that way. I lose my presenter's view, but as long as Christine say we're doing better now? I'm going to just keep going.
Seeing, Walter, we're not seeing your slides. For whatever reason, it's not sharing your slides. It should be.
So. Okay,
That's working. Perfect. Thank you.
we're going to try and minimize that. What do you want me to do with that? Okay. Thank you very much. So the question is, and now, no, it's not advancing now. We're going to go back to it. Yes, we are going to back to presentation mode. It's very hard to read here with the glare. Go ahead. Yes, please. Hooray. To all of you in YouTube land, thank you for your patience. So the question then, why Europa? As I said, Europa is the fourth largest of the moons of Jupiter. It's maybe 10 to 15% smaller than the Earth's moon. This is a picture taken by one of the Voyager spacecraft in 1979. We knew then that Europa was a special place. We knew even before that it was extremely bright. You might think that the Earth's full moon is bright when you look at it in the sky. It looks like it's really immensely bright. In fact, it only reflects about 10% of the light that hits it. Europa reflects more like 70, 80% of the light that hits it. It's a very bright, icy surface covered by these reddish things. The red has to do with the color. I'm not going to get into that, but all of these lineaments turn out to be cracks in the surface. And there are almost no impact craters here, which makes it exceedingly young. So something strange is going on inside of Europa. And we'll sort of talk through that in the first half of the talk. And then we will talk through how we're going to explore it with Europa Clipper in the second half of the talk. So let me start with how geologists learn about geological history on a world that you can't walk on. And the way we do that is that we use basic techniques that were actually worked out by terrestrial geologists a little over 200 years ago. And they have to do with something called superposition and cross-cutting relationships. Superposition you understand very well. If you were ever a teacher or a student in a teacher's classroom and you took a test and the first person put it down and the second person put it down and the last person's is on the top, you can figure the order in which they were turned in based on the sequence that they were there. That's superposition. And you can do the same thing with it in geology by looking at layers in terms of what's there and what's on top of it, and the same process works. And then there's something we call cross-cutting relationships, where if something's there and then it's cut by something later, that something that cuts it must be younger. And so this is a great example. This picture is only about 7 or 8 miles across. It's an exceedingly complicated area. And I'm not going to use a pointer here for those of you in the room because nobody on the YouTube channel will see it. So I'm going to try and do a good verbal description for everybody. But you see that there is a structure, a pair of ridges that go from the upper right down to the lower left. That's one of the younger things because it's on top of most things. But then it's cut in several places and it's on top of other things. And you can start to see that there's an order, one on top of the other on top of the other. And all of this is very young because there are no impact craters here. The moon has been collecting features on it, impacts on it for 4 billion years. And even places that have few craters are usually more than 3 billion years old. We know that from the Apollo rocks. This, almost no craters, probably less than 100 million years old in most places, and yet it's smaller than the moon. Now, why is that weird? There's a basic rule, which again, you all understand. Big things take longer to cool off than small things. Now, you might think you don't know that about planets, but think about how long it takes to cook a hamburger, how long it takes to cook a roast beef, how long it takes to cook a turkey. The bigger thing takes more time to put heat into it or to get heat back out of it. So big things like the Earth hold on to their heat for the age of the solar system. Things the size of our moon has been mostly dead for 2 billion years. Now the question is, why is Europa so active? And we'll come back to that, but something's going on there. That got people's attention in a big way in the late 1970s. And then we got these much better pictures from the Galileo spacecraft, which actually the last one was from as well. This I labeled ice rafts because you can kind of think of that. All of those linear structures can be figured out how they line up. You can put the jigsaw back together, but you can see they've been spread out. Something below the surface is moving things around. Okay, that doesn't happen in very many places in the solar system. On the Earth, we call it plate tectonics. Think about South America and Africa pulling apart and how those two pieces went together once upon a time. And all of the Earth is doing that. Venus did it once, not doing it now. That's a problem for another spacecraft, which I hope to get to do, but we're not talking about that one tonight. Mars has never done this. The moon has never done this. Something's weird about Europa. In this case, what I call dilational bands. Now, I'm going to have to apologize to the folks in YouTube land because I'm going to actually, for those of you in the audience, think about these structures that are stretching from the lower center up to the upper left, and they look like they've been kind of opened like a book. You can look at my hands for just a moment. Open like a book. So again, this is a place where things are spreading apart. Something's going on, moving things around by. This particular image is a little over 200 kilometers across, so say 150 miles. So there's like 10 miles of opening here. That's a big deal. On the Earth, that would take a long time. Plate motions on the Earth is about the speed at which your fingernails grow or your hair grows. It's in that order of magnitude. Think about how long it would take you to grow 10 miles of hair. A long time. Something weird is going on Europa. And then there's this structure. If you think about what scientists might call this, I'll tell you that the first paper written about it called it the mitten. Scientists can be very literal sometimes. Ask the people who discovered Turtle Rock on the moon. This structure is about 60 miles across. And you can see that there are cliffs on the edge. There are from the shadows, you can tell it's uplifted compared to its surroundings by about 600 meters. That is to say, 6 to 7 football fields or about 2,000 feet. This is a high plateau that's 60 miles across. Something is pushing it up. This is probably something hot in the interior that's pushing up on that, and it's surrounded by faults. It's rising up. At some point, it will cool off and it will sink back down. And then we can look at impact craters. I told you there were not very many. In fact, I should go back. There are just a few very small craters in this picture. Okay, heck, I'm going to break my rule sorry to those of you on YouTube land. Or not. Let's see if the cursor will work. There's the arrows pointing at a little crater. There might be one or two others here. Let me go back one more. There's a little crater. You're getting the idea there aren't very many of them? I promise you, if you look for these on the moon, you'd find them everywhere. In fact, the Apollo astronauts, even in the smooth, flat places, had to work to find spaces between the craters to land their lunar modules. On Europa, not very many of them. So there are some. 3 out of the 4 structures here, with the exception of the one in the lower right, are all about 20 or 25 kilometers across. So think 15 miles. Think from here to the north side. For those of you in the local audience, think from here to the north side of the 6th loop, more or less. These craters look, especially the one in the upper right, look rather like craters do on other bodies. What that says is that when this thing hit, it could not feel, it felt like it was a solid body. It did not feel, because I'm going to tell you in a minute that there's probably an ocean on Europa underneath the surface. But these things that probe down to depths of 5 or 10 kilometers didn't feel the bottom. Now they're starting to get a little funky. There's those on the left. The one on the lower right is about 100 miles across, a little bit less than that. It definitely felt the bottom. It knows that there's an ice shell and that there's water beneath it. It's not solid. That's a very weird impact structure. If it wasn't circular, I wouldn't know what it was. But to make something that big and circular, pretty much the only process we know in geology and planetary science is impacts. That structure felt the bottom of the ice shell and the ocean beneath it. Okay, one more thing. These are a pair of pictures from the Hubble Space Telescope. The moon is superimposed for geographic reference, so you know we're looking at the same piece of Europa 2 different years. And there's this bright structure coming over the horizon. Now, these are noisy pictures. It's the nature of you want to get the picture before it moves so much it smears. So you're working with limited light. So you can see the kind of the background texture, but these structures that are labeled plume in both cases are distinctly brighter than the surroundings. These are not noise in the pictures. And just to be sure, like good scientists, they said, oh, we tried it once. Let's try looking there again 2 years later. And gosh darn it, they found it again. This looks like something coming up from the interior of Europa, jetting gas probably up above the surface. Now, if that sounds weird, we've seen exactly this happen at the moon Enceladus at Saturn. The Cassini spacecraft actually flew through those jets. We actually dive bombed it and actually flew through it and measured the gas. Maybe someday we'll do that at Europa. Don't really know. Something's going on here, and I don't know exactly where this structure is because the fact that I'm seeing it over the edge of the spacecraft of the moon doesn't mean it's there on the edge. It might be behind the edge and just jetting it up high enough that we can see it. So I can't tell you exactly where it is, and I can't really target the spacecraft based on that. But it's another suggestion. And this is an artist's rendering of what that might look like. Okay, we've never been there that close, but we see jets like this on at least one other moon on the solar system called Enceladus at Saturn. And I promise if we see this happening on Europa Clipper, it's going to get everybody's attention real fast. So what we think is going on here is that there's an ocean inside of Europa, not at the surface. The surface is really cold. So the outer part it's water ice, and it's well frozen much more severely than what your freezer can do at home. But below it, it gets warmer, and we think it has an ocean of liquid water and all kinds of other stuff mixed in it. Salts and sulfates and all kinds of good things that might like to live would like to chew on. So this is a artistic rendering of that. The central gray spot is the core of Europa. It's made of the core will be mostly metal. Below that, the brownish area shown in the 3D cutaway is rock. And then the outer part is water, an icy shell of uncertain thickness that we'll talk about, and then a layer of liquid water. And that explains, we think, what we are seeing here in all of these observations, why things look like they are moving in a way that's even more dramatic than motion of plates on the Earth. Now, I will tell you that the plates on the Earth are moving over a solid mantle. We don't have to guess about that. We know that because of the way seismic waves go through it. This is an absolute solid certainty. Any first-year geology student, if they don't answer that question correctly on their oral exams, probably doesn't get to be a second-year student. It's the way it is. It's a basic fact about the Earth. We don't know that, and actually sending seismometers there is going to be a real challenge. But we see the evidence of these things moving around, like those ice rafts, or like the craters, in some cases, feeling not a solid bottom, but a liquid bottom that changes the way they behave. And then one more piece of evidence is that we flew by this, by Europa with the Galileo spacecraft enough times with a magnetometer. Now, Europa doesn't make a magnetic field. It doesn't have a north and south, but Jupiter does. And as Europa moves through it, one of the basic laws of physics, Maxwell's laws, tell us that if there are moving electric charges in a magnetic field, they will make their own responding magnetic field. Now, solid rock is not going to be electrically charged, but things like salt dissolved in water breaks up sodium and chlorine. Sodium is positively charged, chlorine is negatively charged. Now you have electrical charge, and in an ocean, things move around. So you have all of the conditions there, if you're moving through the Jupiter's magnetic field, that Europa distorts the magnetic field in ways that we can recognize. So we are pretty darn sure that there's an ocean there. What we are doing is not going to Europa to see if there's an ocean. We're going there to characterize it and to learn what it means for the interior. And so this is, again, it's an artist rendering. One thing we don't know is how thick the icy shell is. Some people say it might be exceedingly thin, and most of what's going on there on the left would be things going on in the liquid water. You might have volcanoes producing hot plumes, interacting with the surface. And then other people would say, no, there's probably a thickish 10, 20, 30 kilometer thick layer of ice, which might have things going on in the interior that we call convection. That's kind of the view where I'm at. But figuring out how thick that shell is one of the things that we're supposed to do. It's one of the things my team is supposed to do. I say my team as if I'm the one that put it together. I'm not. I got selected to be on the team kind of late, but that's okay. I'm there. But you know, it's somebody else's team, and I get to play ball with them, which is going to be, as Alan said, it's really kind of cool. So we're going to send a spacecraft called Europa Clipper. This is a picture of it being put together at the Jet Propulsion Lab in California, shortly before it was shipped to to the Kennedy Space Center. The big ovalish structure, let's try this game again. This is the radio antenna, the main radio antenna that will send things down to Earth. I don't know if the foil covering will ever come off. It's there to keep it from getting too hot while we're close to the sun. I don't know if it ever is released or if it stays exactly like that. But for comparison, look, there's a person. There are several more people. This is a big spacecraft. And it will, so the antenna is big because we want to send a lot of data back from a long way away. So we have to have a big antenna. And what you cannot see here are the solar panels. We need electrical power to power the spacecraft. And these are monstrous solar panels. They're the biggest we've ever flown, the biggest NASA's ever flown. Now, I have to clarify that because I will not pretend to know what every spacecraft that every three-letter agency in the United States government has ever launched. They're not going to tell me. And if they did tell me, I couldn't tell you, or else they would, well, it would not be pretty. But this has electrical panels on it, solar panels, like the kind of solar panels you can put on your roof, probably more, better efficiency because you don't want them to be too big. Even as it is, if you put this spacecraft at the midcourt line of an NBA basketball court and you spread the panels out, and you really don't want to do that because they will collapse under their own weight in gravity. They would cross the end line at both ends of the court. They are that big. This is a 100-foot long spacecraft. It's massive. NASA's never flown anything like this before. May never again, for all I know. Certainly not in my lifetime. Anyway, NASA spent years putting this together and building a science team to go with it. I'll tell you about the instruments in a few moments. The spacecraft launched October the 14th. We were supposed to go up on October 10th, and my wife and I had every intention of being there. And on the Sunday morning, we were supposed to fly out there. I went downstairs and said, honey, we're not going. She looked at me like, what do you mean we're not going? I said, there's this thing called Hurricane Milton, and it's now category, and it's aimed right at Titusville, Florida, which is, well, just outside of Kennedy. So that was Sunday. The science team meeting kept going on anyway for the people that were willing to fly into it. And, you know, for those of you in the room, many of you remember Hurricane Beryl last year, which was not even that big. I had no intention after living through Beryl to fly into the path of a Category 5 hurricane. Just wasn't going to happen. It falls in the category of mama didn't raise no dummy. So after it happened, and I was getting reports in real time from people as this was going over, and somebody sent a picture of the roof coming off the bank across the street from the meeting hotel from a tornado spawned by the hurricane. And they thought, oh, they escaped a close call, until the next morning when they went outside and they saw that the hurricane had clipped the corner of the hotel we were supposed to be staying in. At this point, I'm thinking, I'm actually kind of happy to be here. And then people are saying, well, the hurricane's over, we're going to fly there. And I'm thinking, you've not lived through a hurricane. One day after Hurricane Beryl, none of us were ready to have visitors, were we? No. In fact, many of us didn't have power back. So Kennedy gets things organized, and 4 days later, they're ready to launch. And instead of watching it in the bleachers, we watched it on NASA TV. It was still pretty. It wasn't just quite as exciting as doing it with, you know, thousands of my closest friends. But there's the launch. There's the spacecraft separating from the rocket, and all of these pieces. Right there's the antenna. That's not what I wanted to do. Let's go back. All of these pieces right here and right here are the folded up solar panels. They're going to deploy an hour after they launch. They deploy just perfectly. Everything has gone swimmingly in the last 8 months. Taking no chances. So we're on our way. It takes a long way to get to Jupiter, many years. We actually flew by Mars on March the 15th, I think, sometime in early March, because we used the gravity of Mars to redirect us and speed us up a little bit. And along the way, we used it as a target to test a couple of our instruments. But mostly we were using it as a gravity assist. It's going to fly back to Earth at least once. I think just once, but maybe twice. I've lost track. And we will eventually get there on April 11th of 2030. It's a long way. The solar system's a big place, and it just takes a long time to get there. Even with a really big rocket moving you really fast, it just is a slow process. So now I'm going to transition into what are we going to do when we get there. And if you want to have an instrument or a whole mission on a NASA spacecraft, you have to have science goals and objectives. You can't simply say, gosh darn it, it would be really cool to send a nice camera out there. What are you going to do with the camera? What does it need to have? What capabilities does it need to have? How will you know if it's good enough or if it's too good? Too good is, yeah, I don't know if there could ever be something too good, but you don't want to design something and pay for something that is more than you need or more than the data you can send back. So you have to have explicit goals for what you're going to try and do, so you can then test whether your instruments suite will help you answer those questions. So Europa Clipper has one goal: to explore Europa to assess its habitability. Now, we're going to be around Jupiter. There's going to be all of these other moons, and you know what? We will pay attention to them only incidentally, because this is already an expensive mission, and to divert our attention to other things beyond what we're trying to do would just keep us from doing our main mission. So we're going to look very focused way at Europa and not spend very much time thinking about all of the other cool stuff in the Jupiter system. Just the way it is. It's the way we have to save money. We have 3 objectives that are meant to answer the overall goal. One is we want to characterize that ice shell, any subsurface water, which means that ocean that we think is there, and the nature of the exchange of chemical things between the surface, the ice shell, and the ocean. How are chemicals moving around? Because that influences the potential for life. The second is we know that the outer part of the ice shell is mostly water ice. We know that from the way it reflects ice, what we call its spectrum. We want to identify the composition of non-ice materials that are there. And then we want to characterize geologic surface features, in part because they'll help us figure out what's moving back and forth, but also because someday NASA's going to want to send a lander there, and we're going to want to be able to say, where is it safe? If you got the idea that there's a lot of places that are pretty rugged, well, you got the right idea. And so finding a safe place might be challenging, but that's what we're going to do. Those are our three objectives. Now, the best possible way to do this would be to say we're just going to put our spacecraft into orbit around Europa. There are two problems with that. One is Jupiter's really big, and as we get close to Jupiter, it speeds us up. And to slow us down enough to go into orbit, we need a lot of rocket fuel. And as big as that rocket was not big enough to send the fuel we would need to. The second problem is Jupiter has this really intense radiation field. And if we spent all our time right around Europa, deep in the radiation belt, spacecraft would be dead in a month. That's a bad outcome, just saying. So what instead we're going to do is we're going to put the spacecraft into an orbit that it comes back to the same place every 3 weeks. Well, why 3 weeks? Well, Europa is in a almost perfectly circular orbit. Not quite circular, which reminds me, I forgot to tell you why Europa's got this going on. Europa and the other moons go around in what's called a resonance. They pull on each other, and it's not quite a circular orbit. So Europa is, again, sorry to you, those of you on YouTube, you're not going to see my hand gestures, but the spacecraft flexes a little bit out and a little bit in, a little bit out and a little bit in. So you can imagine rubbing your hands together. That doesn't warm things up very much, but imagine rubbing your hands together like that for 4 billion years. It'll warm it up, I promise. So that's how this happens. The tides on Europa that are related to its interaction with the moons around it are the heat source. And now what we're going to do is, Europa goes around once every 3.5 days. We're going to come back to the same place every 21 days, a factor of 6 longer. So most of the time we spend far away from Jupiter, out away from the radiation, and we don't have to slow down near so much. And then every 21 days, we get one really good close-up view of Europa. Now that doesn't sound like it's a great trade-off, but in fact, over the course of 4 years, we're going to essentially dive bomb Europa in about 49 different places. We're going to imagine it's going to come in, it's going to get down as close as 25 kilometers. And all of those green places, yes, all of those green places are the places where it's going to be less than 100 kilometers off the surface. So most of Europa we will get close to at one time or the other. And where the interesting places are, and we've designed this tour to really cover the details of Europa very thoroughly. It's not a perfect mission design, but we can't afford, this is what we can afford, and this is going to be a truly stunning mission. So I said we are going to try and understand whether or not Europa is habitable. I'm being careful about that in much the same way NASA is careful about saying we're looking for life on Mars. We are assessing whether Mars could have supported life once upon a time. We are not looking for life now because it's too easy to fail that, because you actually, if you don't find life, did you fail? Or was there never life there? Or did you go to the wrong place or whatever? But you can look for whether it was habitable, whether it meets the conditions for life as we understand it, as biologists on the Earth understand it. Well, there are 3. One is there liquid water? Almost certainly the answer to that question is yes. If we don't find liquid water with our instrument suite, it will be the stunning disaster of the century for science, because every indication is there's liquid water there, and we're going to probe it very thoroughly. I'll show you in the last few slides. The second is, are there key elements that we need to support life as we understand it. Life as we understand it, as molecular biologists would teach us, depends on the way a few important chemical elements bond together. Carbon, most important, because it has more bonds and more versatile bonds than other element in the periodic table. Hydrogen, oxygen, sulfur, nitrogen, and phosphorus all play roles in how they put this together. And as it turned, and I put sponge there because, okay, that's not what those, I wrote them out in the order that we think they're important. But when I was first learning this 20 odd years ago, on a field trip that I helped lead, in fact, Alan Treeman was with me on that trip. The astrobiologist we had with us said, you know, I was looking at a store getting ready his, getting snacks, and he found a snack called sponge, some kind of a snack take. And he put a picture of that up there so that people would remember the important chemical elements. And it evidently worked because it's not going to ever go out of my brain. It's like the song to the Brady Bunch, which my daughter never really understood why I sang to her every morning when she wouldn't get up for high school. Another piece of my brain that will never be released. So we know that carbon is there. We'll start hydrogen and oxygen, that's water. But we also know from our observations that carbon and sulfur are there. We can guess there's probably nitrogen and phosphorus, but we have not proven that. So we're going to be looking for all of these elements. If they're there all together, that's another big step towards being able to prove habitability was possible. Doesn't mean there was life, but it means it could have had life. And then there has to be a source of energy, one or more sources. On the Earth, the biggest source of energy, of course, is sunlight. Plants take in the sunlight, they photosynthesize, and then the carnivores eat, actually the herbivores eat the plants, and the carnivores eat the herbivores, and it's the whole cycle of life. On Europa, we're looking, and actually in places on the Earth, there is life in all kinds of places on the Earth that we didn't know about 30 years ago. When I was going to school, we thought there was a lot below the surface, was kind of dead. Turns out not to be true. At ridges in the center of the oceans, there are what we call black smokers, hot water coming out with all kinds of living things in them. Underground, there's energy sources. So we're going to look for energy sources, chemical sources of energy mostly. Those are the things we're going to look for. And the question is now is how? Well, okay, for starters, we got to ask the question, what kind of conditions might support life? On the Earth, most life is in a small range of conditions. This chart shows pH from like 0 to 14. 0 is battery acid. Most living things don't like living in battery acid. 14 is really strong bleach, and most things don't like living in bleach either. But there are things that do. And then the other is the temperature. And you know, most things like being at around 25 degrees Celsius, kind of like what's around here. But there are things that live in hot springs. There are things that survive in boiling water above 100 degrees Celsius. And there's life that manages to survive where the water is completely frozen. So life thrives in many conditions. We could add to that, you know, what is the amount of salt? Most life likes it. It's not very salty, but there are things that love salt at a level that I promise would kill you. One glass of really salty water could destroy your kidneys, and that's all she wrote. And then one more is the radiation environment. Most things on Earth don't like being around a lot of radiation. Your doctors don't want you taking your chest x-ray every day for the rest of your life. Not good. You don't want to live inside a nuclear reactor, but there are things that can. So life thrives in an awful lot of conditions on the Earth. We're not going to look for the living things because bringing that kind of equipment, not sure what you're looking for, would be really tough. But we're looking for the conditions that could support it. So 3 things that we're trying to do. One is, I told you at the beginning, we had 3 objectives. So I'm going to lay out the instruments based on those objectives. Oh, and accidentally I put gravity first because oops, that's my experiment. Sorry. But we said we were going to look at the interior structure of Europa. One of the ways we can measure the structure of that ice shell is by looking how it deforms. The Jupiter will raise a tide on Europa as things move in and out. And that shape changes a little bit. And the easiest way it turns out to measure that is to look at how the shape of the gravity field changes. That turns out to be pretty easy. So we're going to go looking for that. We have a magnetometer that will look for a magnetic field. And remember, I told you that Europa doesn't have its own magnetic field. It doesn't have north and south, but it responds to Jupiter's magnetic field under a variety of different timescales. And so we're going to measure all of those timescales, which when we did it with Voyager, we could only measure one timescale. So we're going to learn more about the response. And in fact, the strength of that magnetic variation will tell us something about the chemistry in the interior, because the more electrical charge is there, we will have a stronger magnetic response. And then there's a radar. And you might think radars bounce off of the surface, but certain kinds of radar can see right through the surface, can go kilometers down through ice, and then reflect off of something else. And we're going to try that. It worked really well, actually, at Mars, apparently. And we're going to detect those reflections. And all of that data together, each one of these experiments has its limits. But when we stack all of them together, we are probably going to get results that are far more profound than we can get from any one of these. The second thing we said, we wanted to understand the composition. So we're going to send spectrometers, things that look at light at all of its different wavelengths. Think about how you take white light and a prism and you break it up to red, yellow, green, and blue. Well, it's not just that. It's the ultraviolet light that gives you a sunburn, the infrared light that makes your TV remote work. We're going to measure all of those things. And the way things get absorbed at different wavelengths tells us something about the composition. Then we have a mass spectrometer. At Saturn with the Cassini spacecraft, I told you we dive bombed through the Plume. I don't know that we're going to be able to do that at Europa, but we're prepared in case we get that chance. We're going to directly try and measure the composition of the gases coming out of Europa. And then we also can measure charged particles around Europa and dust that's coming off it. So we have ways of directly measuring, not just indirectly, but directly measuring the composition. And maybe even some of the organic things. This could be really cool. And then finally, we want to understand the geologic history. We're going to map the whole surface at a modest resolution. A modest resolution probably means 50 or 100 meters. So each pixel is the size of a football field, but we're going to measure it in a bunch of different wavelengths, and then we're going to have high resolution pictures of selected areas. Turns out that's a better approach. Getting context for the whole object and the colors of the whole object, plus selected high zoom-ins, is a better way of getting things than just saying we'll just get zoom-ins or we'll just get the low res. And then we've got an infrared, another infrared spectrometer that will look for regions of elevated temperature. Because if there's hot water near the surface, something erupting as a plume, we should see it. And again, that will get our attention pretty quick. So that is, I think, the last of it. It is. That's what we're going to do. It's a big, monstrous spacecraft with a humongous science team. I'm thrilled to be a part of it. My wife in the audience will tell you that I was bouncing off walls the day I came home saying I had got on. Because, you don't get this opportunity very many times in planetary science. And so it's a thrill to get to do this. It's part of my retirement plan. At some point, I will say I'm done being a director, but I'm not going to ever be done being a scientist, not until they call me off. At this point, what I'm going to do is I'm going to try and answer some questions. Yolanda and Grace, I'm going to assume you're going to take mics around. Is there anybody else who can help? Because we're also going to be looking online. Alan, can you help with that so that somebody can read the online questions? And I'll start with folks in the room, but I will take a break to give people online a chance. And I'm going to switch back and forth. And at the end, we'll go out there. There is food out there, if you didn't see. And I will answer some more questions when we're outside. And somebody, Grace, I don't know where Grace is.
Grace is out.
Okay. Somebody will have to tell me, well, just when it's time to start.
I'll read the online questions.
Okay. Oh, thank you, Christine. But somebody will have to tell me when we should stop because you wind me up and I just keep going. So let's find the first question. Alan, do you want to pick somebody?
This gentleman here.
Oh, okay.
What is the timeline?
The timeline. So we launched last October. It will take us 6.5 years to get to Jupiter. We go into orbit on April 11th. If I had looked it up, I could tell you the minute we're going into orbit because Isaac Newton is in the control seat here. If we either go into orbit or we don't, but it's on April 11th, I believe, of 2030. It will take us about a year to squeak the orbit around so that we're going by Europa frequently. And then for the next 3 years at least, we will be making repeated passes. Probably at the end of that time, the spacecraft will still be healthy and we'll say to NASA, you know, give us some more money and we'll give you some more data. That's the way because once you're there, you don't want to stop. At some point you have to because you got to let the next things go. But it's unlikely that we will stop doing science in April of 2034 because the spacecraft probably will still be answering good questions. Okay, next question.
Hi, how long does the data take round trip? So what's the travel time and can you expand a bit more on the telemetry on it?
So the data will travel at the speed of light. Jupiter is about 5 times as far away from Earth as the sun is. And it takes about 8 minutes for light to get from the sun to the Earth. So that might sound like 40 minutes, but in fact, the Earth and Jupiter move around. So sometimes it might be 40 minutes, sometimes it might be a couple of hours, depending on which side of the solar system we're on. But we're talking about a fairly short period of time. What we will do operationally is we will take all of our data while we're flying by Europa. We're focused on Europa. We're not sending any data down. We're storing it on the spacecraft. And then in those next 3 weeks, we're radioing it back a bit at a time. And I think we'll get it all back before we take our next dive bomb at the planet. Okay, next.
We have a
Are there any
question.
goals?
Go ahead. We'll do this and then we'll take one from online. Go ahead.
Are there any goals or is any of the data you're gathering in this spacecraft designed to kind of pave the way for a future landing spacecraft? Is that part of your goals for this mission?
So we will take very high resolution pictures of some areas of Europa. I'm not on the spacecraft camera team. They really don't want me interpreting the pictures. They really, really don't. I'm good at equations, which is what I need to do for the gravity. I'm not so much good at, I'll let somebody else figure out what the geology is. But yes, they will certainly be looking for places that are likely to be safer. I'm not sure we can ever say that someplace on Europa will be safe, but safer than other places, and whether it's good enough for NASA, I don't know. Okay, online?
We have 3 questions online, Walter. The first question is, can you change flybys slightly if you spot a geyser?
Very good question. Question for everybody was, can we change the trajectory a little bit if we see a geyser? And the answer is probably in our main mission, we are probably locked in. Let's see, the spacecraft tour we are using now is Tour 31 version 7. They did a lot of calculations over a bunch of years to find things and for us to optimize it. Because every time we fly by, Europa tweaks us a little bit and we've got fuel to optimize with that, but we can't, if we change where we go, we change where everything happens afterwards. So probably we are not going to change during the prime tour, but as we get into the extended mission that we hope happens after 2034, much more likely we'll do that. And this is different from Enceladus. Enceladus at Saturn is a tiny, tiny moon. It's small enough that it has almost no effect on the spacecraft. So we could park it where it wanted to go and it didn't change what happened after that. We used Titan, the moon, the biggest moon of Saturn, for that. For Europa, I think the first few years are probably locked in. I mean, if we found something that made us want to change it right now, maybe we could change it, but I'm not even sure of that because I sat through years where we are going to go. I think I came on tour 22. And, 10 changes of the tour and multiple iterations of the last one. I think that probably we're not going to change, not right away, but eventually, probably yes. Okay, next one.
Okay, the second one is when the Clipper flies 25 kilometers or so from Europa to sample Plumes, could minerals or compounds stick to its solar panels, reducing power capacity and risking the mission?
So we're going to fly that low because we want to get close-up pictures. The density of the material in the plumes is probably really, really small. So I don't think it's going to be something we've got to worry about. Plus which there's nothing else in space around you. So even if you got a liquid drop on your solar panel, it's going to want to sublimate into the space around you. So I don't think anything will stick and cause a problem. And if the engineers thinks otherwise, I defer to them.
Well, we are running out of time soon. So there are 3 others, and I think
Well,
there's one gentleman
we'll
here.
take one more here, and then we'll try the room for a couple more. How's that?
That sounds great. The third question, how does studying Europa help us innovate or better understand Earth?
Good question. So Europa is obviously a very different place than Earth is. But we don't understand how life originated on Earth either. We understand a lot about how it functions, the chemistry of life, the biochemistry and things, but we don't know exactly how life originated on Earth. Understanding how it might work in another place would give us a second way of looking at it. And I think that would be really profound. I'll point out, for those of you that might remember now, almost 30 years ago, NASA made an announcement in the summer of 1996 about having found life on Mars. And there were a group of scientists, including some working at the Johnson Space Center, who looked at a meteorite that we know is from Mars and thought they found things like fossils and chemical signatures of life. It turns out that, boy, it was controversial from the word go, but scientists took it seriously, and in the end, we've decided it's probably not true. But it got people's attention because it was a second way of telling us what is potentially how life originated. And that's a profound scientific question. It's one of the most profound questions I can think of, in the field of science. We won't answer it directly because, as I say, we are not looking for life. Bugs could hit us and we couldn't characterize them because that's not what the spacecraft is designed for, because we don't know enough about Europa to design an experiment to look for that. We actually sent life detection experiments to Mars in 1976. 49 years later, we still argue about what those results mean. It's hard to do things by remote control in a lab that you can't adapt. To do that, we probably have to bring samples back, and that's going to be expensive, and it's not going to happen in my lifetime. Okay, Alan, do you have another one?
Hi, I have a 2-part question. How much input from home and monitoring does Clipper receive while it's in transit? And then is it in sleep mode on its way, or is it capturing anything?
So we're not actively using the science experiments. The engineering team, monitor every day the health of the spacecraft. I'm not sure it's continuously in contact with the Earth, or if it contacts once a day or something like that. I get to see a report once a week, which is enough for me to go, okay, it's healthy, that's good. We got them every day for a while afterwards, and by the end I'm going, okay, do I have to read these reports every day for the next 6.5 years? Yeah, and that's a kind of a weird question to ask about a spacecraft that I've been dying to be a part of. But at some point going, yep, today it's still alive. Yep, today it's still alive. I'm glad there are people doing that, and they monitor things. We're not taking data with the instruments because that would mean paying scientists to analyze that much more data. And NASA, and this is not a comment on the current presidential administration. This was the plan going back several years. We are focused on our science goal, which is to go to Europa. And even though there are a lot of things we could do with this spacecraft while it's en route, we're not doing them because it adds complexity. It adds operational expense to the engineers. It adds science expense. And that's not what we're there for. We will probably collaborate with the European spacecraft called JUICE that is on its way to the Jupiter system. We will be there at the same time. We will probably do some joint observations, but even that is being negotiated right now. It's not yet fully worked out.
My question is, what is the resolution of the primary science instruments on board the spacecraft, if you know the numbers off the top of your head?
Well, resolution for most of these things is a function of how close you are. And I'm going to get, and I don't know with certainty. So I'm a scientist. I have to characterize my not certain. But, you know, I wouldn't be surprised if the best pictures when we're down at its lowest altitude might be a meter or a few meters across. That's based on what I know about similar camera systems. I don't know with certainty what we can do, but something like that seems likely. I saw a picture when the infrared radiometer that looks for heat signatures was first tested out. They took it up. It was built at University of Arizona. They took it up on the roof of their building. I was in that building actually just a couple of weeks ago, not up on the roof. And they took a picture of the surroundings as the sun was setting. And so you could see all of the lights and all of the buildings starting to come on from their heat signature. So that was a great indication that that instrument worked really well. That's the kind of things we can hope to do. And you know, when we're 100 kilometers away or 1,000 kilometers away, the image resolution will be less, but we'll see more of the surface. So there's always that trade-off. You want to see the whole surface as much as you can. With Galileo, we were supposed to get the whole surface, but that antenna did not deploy properly. It was folded up, and when it deployed, it kind of was bent. And so we couldn't return data with the main antenna. So we didn't get full coverage of the planet. For this spacecraft, we will get full coverage. And that antenna, we don't have to worry about. It was sent in its full open 15-foot, 5-meter glory. But we'll be looking, you know, to get the whole planet at maybe 50, you know, the size of a football field more or less, and then selected places at much higher resolution. And that's just the strategy going in, is that you kind of have to do some of both. I don't know if that's really the answer to what you're looking at. That's the best way I can put it to a lay audience, is to talk about the camera. Good enough? We're probably looking at 1 part in a million, more or less. The variation in the gravity field with respect to using the level of gravity for the Earth, which I know, and we know it for Europa. I just don't have that number plugged into my head. But given the uncertainty of what we're going to do with respect to the Earth's gravity field, I'd say 1 part in a million, which is why we can measure the change in the shape as it flexes. You really have to be that good in order to do it. Okay, is there anyone else online?
We have 2 others, but it is 8:29. So maybe.
Okay, let me ask, are there any children in the room? And is there any child who would like to ask me a question? I don't bite, I promise. And maybe there's not, but if there's a child who is willing to take it, I see we've got a volunteer. This is going to be the last question. For those of you online, I'm sorry, but I like giving kids the last word. Yes.
Bridgewater. So why is Europa your target?
Good question. We have been we looked at all of the moons of Saturn with a spacecraft called Cassini that orbited Saturn from 2004 until 2017. So we've studied Enceladus very carefully. Europa has not been studied nearly so much, in part because the spacecraft that went there, as I said, the antenna didn't work properly. And I told you Cassini didn't work, we stopped exploring in 2017. One of the things we do not want to do is inadvertently contaminate these moons with things from the Earth. So with Cassini, they invented a plan to fly it closer and closer and closer and closer, because then they were measuring the gravitational field of the clouds, to get to your question about how precise it is. And eventually it was allowed to crash into Saturn, to burn up. We will do something like that with Europa Clipper at the end. The current end of mission plan at the end of 53 flybys is to crash it into Ganymede, where we don't think there is life, so that we don't accidentally let it crash. If we leave it in orbit, untended, with no controls, it will go where flyby, and at some point we'll not be able to predict where it's going to go, and there's a chance it hits Europa as opposed to one of the other moons. We don't want that. So we've got a plan to crash it into Ganymede. Except that we are counting on the fact that NASA is going to say, you know what, don't crash it just yet. And we have a plan to keep going after that, just if we get the money. So that's the plan, and we'll stick to it. And ask me again in 2034. Thank you so much. I appreciate you've been a great audience. Our next one, 2 weeks from yesterday, June 30th happens to be what we call Asteroid Day. This is the named for a meteor that hit in the Soviet Union in 1908 called Tunguska. And so this is going to be about how NASA is studying this. Paul Abel is a local expert from the Johnson Space Center. He'll be giving that talk. We're having one more of these, we think, in September, probably about one of the Mars rovers, but I don't know the topic. I know who the speaker is going to be, and I don't know the date, but I'm going to guess that Laura is probably going to plan to talk about one of the Mars rovers, because she's on one of those instrument teams. Look forward to seeing you again, but right now there is food out there, and I will make my way out there soon. Thank you very much.